Hey, welcome to the afternoon session. I have the pleasure of introducing Katrina Barron of University of Notre Dame, who will talk about rationality of C-graded vertex algebras and their applications.
Thank you, and thank you for the invitation. I'm enjoying this immensely. I'm only here for a week, unfortunately, but I thank you to all the organizers. I have the absolute pleasure, I'm the messenger here for a group of young and researchers that Gewali Yamskulna and I put together through the work, and the real thanks here goes to Ana Rose Camachos and Nejla Agahi for starting a Women in Mathematical Physics program through VAMP. We put together this group, Gail Yamskul and I, these are all postdocs now. I think Veronica Pedic-Tomic started off as a graduate student when we started working. And so we're starting to get results. We split up into kind of two groups that after we decided to work on certain areas. And this is the work that was mainly headed up by Darlene Adabo, Veronica Pedic-Tomic, and Gewala Yamskulna at first. And then when they started getting some results and having a few gaps and everything, and we needed to get up to speed, we all started working together on this. But it has, a lot of it came out of Veronica, gave us the example of her very good work with Dražan Adamovic on the beta-gamma systems, Weyl vertex algebras. And so I'll use this as an example throughout, and we'll just dive into this. Okay, so the motivation is to look at different gradings on vertex algebras. So you're outside of your integer grading in general. And we're going to look at conformal flow. So I'm going to pose the results that we have kind of in the context of two stories of conformal flow. And I'll illustrate that by our two free field theories, Heisenberg and beta-gamma system. So that will be one of our applications, too, to picking apart what can happen with the Weyl vertex algebra system once you start putting a conformal structure on it. So very basic examples. So once you start looking at your grading and what types of gradings you have at your disposal, then you want to start talking about, well, which modules do you want to talk about? In particular, we throw around this word admissible. Oh, we'll take the admissible modules. But depending on what context you're in, what do you mean by admissible? That's the big question, right? And in particular, what class of modules hang together in some nice way. So we have to discuss that, modules. And then I'll present the main theorems, and then I'll run out of time, and we'll quickly go through the the machinery, but it's standard W-algebras, but for C-graded vertex algebras, and then filtrations and finiteness, meaning a type of C2 space in which you grade your W-algebra and put it inside this Poisson-type algebra to get something about dimensionality for some nice class of vertex operators, vertex operator algebras, C-graded in this case, and then we need an extra theorem to prove our result. But that's where we're going. Stop me if you have questions. So, okay, so classically, we think of Z-grading or maybe half Z-grading, bosonic, fermionic. Interestingly enough, I'm not doing any fermionic stuff today versus my past work, but, and then modules. So what do we mean? When we have some kind of Z-grading or half Z-grading, we're thinking of admissible as being n-gradable, or 1/2 n-gradable. Right, that's some kind of positivity condition on the grading. You might have Q grading because you might have twisted, right? Okay, so let's talk about this, about now, once you start talking about conformal vectors. So for the Heisenberg, you have the standard conformal vector, 1/2 alpha minus 1 squared, but then that's the usual one, but then I can add in alpha minus 2. In that case, it's a non-quadratic element, so physicists might say, I don't want to look at that. But we see that this is a very important setting for the bosonic theory, because in that case, we can, only when we have a non-trivial A are we going to be in the setting of looking at larger rational lattices in which we can embed some kind of theory and then take some kind of kernel of screening operators, for instance, and construct the symplectic fermions, right? So we use this all the time. You've seen both of these throughout. I mean, ever since day one, we also dealt with this free field theory. Actually has appeared more than boson. Ever since David Ridout's talk, and even today, I think every day we've been dealing with this system too. So we'll talk about the conformal structures on this one. Think about what happens if I conformally flow. So in this here, I have some A. This is the A plane. So I have some parameter, and as I flow with respect to this conformal structure, this thing is a VOA the entire time. It's a Z-graded VOA. The grading is not affected by it. Are the modules affected by it? So its U-algebra is just C adjoin X, right? It's the U-algebra, if you think about it. I can think of the X as being that. It doesn't change. And in fact, in this setting, all of the indecomposability, non-irreducible setting for logarithmic theory is completely seen at the level 0 U-algebra. Everything happens in the vacuum. All the indecomposability, non-irreducibility happens in the vacuum. But when you flow, does the structure of the modules change? And only in one instance can you change from being L0 not acting semi-simply to L0 acting semi-simply, and that's when you're with a module whose weight lambda is equal to A. And only if you have a 2 by 2 Jordan block. So there's one time where the some structure that we might care about the modules changes in this picture. Otherwise, it's just me. Okay. I think I just said what is written there. The central charge changes, but that doesn't change anything. I have the central charge 1 minus 12a squared. Okay, fine. Important for free field realizations of irrational C2 cofinite. Very important, right? But I'm just pointing out some of these things that we know about it. I already said that. Okay. So you have other free field theories in the Heisenberg, right? You have free fermions, you have beta gamma ghost systems, you have the BC ghost systems, this has been said before. Free fermions and the BC system are so nicely behaved that they're almost boring. So I was surprised, and I was taken out of my comfort zone in general with this beta gamma ghost system. If you're a physicist and you always think of beta gamma ghost systems as central charge 2, we're not going to. Okay. So our main result in particular applies to central charge non equals 2. That's using the usual conformal structure. Okay, so more generally, we're going to define a notion which has an awful name that we inherited from another paper, and I think we're just going to change it because it's terrible. Strongly finitely generated C real greater than 0 graded VOAs. Okay, these are just going to be the very nice C grading VOA type things, okay? And I'll refer to them as that because I can't even say this. So we're going to build up this notion. And what we're going to prove is that these types of vertex algebras, so they have a conformal structure, they have some kind of nice positive sense of their complex grading, but everything's complex graded, which took me a long time to really understand. I think I understand it now. These kinds of things are going to have, and you have to define the notion of a J algebra in the setting, that's going to have trivial J algebras. So there's going to be one simple. And furthermore, it's completely rational. Now this is opposed to what we will see for C equals 2. In fact, we've already seen that discussion of the work of, I think it was first Ridout and Wood, and then Allen and Wood now have a class of indecomposable modules for C equals 2. It's highly non-rational. So this is non-rational, but everywhere the lack of rationality is completely the same, and maybe only the logarithmic nature changes at one small point at one blip. Okay, but this setting you can move all over this place, and the vertex algebra I'm going to be taking is going to be the same. You still have all these modules, it's just the way you characterize the modules under conformal flow becomes completely different. It was interesting. Okay, so here I've written this in terms of these generators, A and A star, beta and gamma usually, but again, we inherited this from some other papers, so we stuck with the AA star notation. So this is already, I guess I took the two-dimensional Weyl-Lee algebra and this is the affinization of that. So there is a unique vertex algebra structure on this. You can see right away, and there's these automorphisms of the affinization of the Lie algebra here, the affine Lie algebra. Spectral flow, and then this is sometimes called conjugation, and these figure prominently when you're analyzing the module structure, like for instance with the work of Adamimovich and Petit-Tomic. Okay, and then you just define you induce as you will from a module, and you get that's just saying it has a structure of a vertex algebra. There's a little bit of strange things with the shifting here, right? I'm allowed to have n equal to 0. So sometimes I'll write it like this, that here I have minus n minus 1 as my underlying space and minus n, and they're allowed to be 0. Okay, and it's a simple vertex algebra. Okay, you have sitting inside there a nice Heisenberg that's generated by, it's a quadratic element even, so physicists would even like it. And it behaves this way with respect to my generators A and A star. And with, so here I took this alpha minus 2 element here. I'm going to take what would normally be then omega. So I would normally, the usual conformal element would be this guy. I guess I'm never acting on the vacuum. I should always be acting on the vacuum. So instead of just shifting, adding something n, I'm going to write a parameter here and add in, I guess the convention is to put this minus mu. So this is well known. And this looks like a singlet, but it is a quadratic. Okay, and then of course my central charge changed, and we get something that you would naturally call. So this is C-graded in general, but it's a C-graded conformal vertex algebra. I'll get into the specifics of that soon, but we have all of these pieces of data that we can work with. +1. And so mu equals 0 or 1, we have C equals to the usual beta gamma system, defined by physicists in the early 80s, 70s maybe, used by them, in a non-trivial way in early days of string theory. Okay. I have a symmetry here, you might guess, because 0 and 1 both give the same central charge. I have this quadratic central charge, and the central charge actually does define your vertex algebra, your conformal vertex algebra. It gives an isomorphism so that you can pick out a unique conformal C-graded vertex algebra by specifying the central charge. So this is just this spectral flow put together with this conjugation gives you an isomorphism here between these two guys and these two guys. So that's why I have here some symmetry about this point right here. This is 1/2. So this is my mu land. This is my A land. There's lots going on. I have lots of pictures drawn on there's nothing going on in the Heisenberg. Okay, so this is the same picture that I'm looking at that I will try and refer to. I need this personally in order to understand the definitions that we have put forward. So this splits the mu plane up into regions that have different vertex algebra structure. So one wants to think the different omega mu, I guess I should put a big mu by this omega, right? So this now, I'm referring to, A minus 1, 1. This is the L0, I guess I should put a mu weight of A minus 1, 1. And that is, what is it? 1 minus mu. 1 minus mu. Whereas A star 0 is mu. And so the problem with the typical place that we work with beta gamma and has many applications is that I have infinite dimensional weight spaces with respect to the grading, right? I can take this star itself a bazillion times. This is a 1, A star 0, A star 0. This is the way you want to think about this, and I don't know, R times is R mu. Okay. So it's not, from the VOA point of view, why would you be working with that one? And there are many reasons. It's one of the places where you have good VOA type stuff going on, but bad stuff in other ways. Okay, we're moving forward. So here's my grading in general. You use right. Okay, so now we are going to define several refinements of the notion of C-graded vertex algebra with this conformal structure in mind. And our theorem is going to apply to the orange diamond region, our rationality. So it says that you have this nice conformal flow from this interesting theory that has all of these oodles of indecomposable modules, and you have to start to try and think about, okay, which ones do I want to put together to try and make some kind of closure under fusion and things like this, and Allen and Wood have done this. But if you flow at all into here, it just becomes almost trivial, completely rational. Okay, so back to our comfort zone. We know what a C-graded vertex algebra is. Okay, so I'm going to use this notation before I even put a conformal structure on. So I've not put a conformal structure on. I'm still going to use just this. I have some grading. I have the notion of the weight with respect to that grading. Okay, we use a lot of work by Jeff Mason with one of his students, Rob Labor, in 2014, where he wants to formalize a lot of this stuff with spectral flow, for one thing. And in his paper, he calls C-graded VA something with a lot more structure. And so we're going to build up in steps what he assumes for all of his C-graded vertex algebra. So when you read this paper, you have to be very careful because it does not mean what you think he means. Okay? So I'll tell you what his is. Okay. So here's the other game that we play in VOAs, and we're used to playing, is that we have all this jus, this classically, with the C2 cofinite, rational theories and everything, we construct this jus algebra, and all of our modules are induced from the jus algebra by something we call the vacuum space, or the lowest weight space. And this is another place where you're in your comfort zone. So this will take you completely outside of that comfort zone. So, and whether you like it or not, so I'm going to focus on that jus story, and I'm going to throw out a huge number of modules that you might say, wait, I want to keep those modules. And that's fine. And you may want to keep certain modules, and you may not want to just be inducing your modules from Jou's algebra. But you should know what you're doing when you're doing it and what you're throwing out and what you're keeping. Okay, so we normally define, and so here I'm going to always focus on some kind of real positivity or real, the real structure, because I have to have some kind of up and down with my grading. And so instead of defining the usual omega space as just, this would normally just be gamma here, then I'm going to focus on the real part, and then this makes a perfectly nice way for us to have a lowest weight space, except for it's not a lowest weight space, right? Okay, we call this thing the vacuum space or the space or the lowest space of lowest weight vectors. And especially if we're doing logarithmic theory, it certainly is not going to be. Or certainly if we have like negative graded spaces or something, it's not going to be. It's neither of these things. And even today we will see examples where this is neither of these things. We'll see an example where this thing is empty, 0. I know, it's just, okay. So they should be called vectors that cannot be lowered without going to 0, right? Because especially if you want to do higher level Jou theory or even Jou theory at this level and see the indecomposable non-irreducibles, you want to have other, you want to have, higher up singular vectors that are giving you your indecomposability, non-irreducibility structure, right? So they shouldn't be called lowest weight because those are higher weight, but they're singular. So that's a bad name. But surely vacuum space. Okay. So this is where the terminology is terrible. This should be called omega graded. This should be, or omega generated. Omega generated. We took the Labor-Mason terminology of strongly generated, and of course you've seen that already. Andy has lots of work on strongly generated, and it means something completely different, and I don't mean that in that sense right here. So I mean omega generated from its vacuum space or lowest weight vectors, which is not a vacuum space or lowest weight vectors. That thing. You with me? So if you can't, if you're in your comfort zone, if you're working with usual VOA theory, you're always in the situation where you take something in your omega space, maybe your vacuum vectors in there, and then everything is just a mode acting on that. So that's what I mean by strongly generated, this unfortunate terminology. We're debating whether to change it in the paper or not at this point. We're working with it, and so no. So it should be omega generated, fine. And then you have the notions of real graded, Q graded, everything, blah, blah, blah. We also, and in a lot of work, and even in standard stuff on Jou theory, which can get you into trouble, and there are some mistakes in the literature on this, we tend to equate the weight grading, even once we have a conformal structure in general, the weight grading and the degree grading, where you're inducing from your Jou algebra, and we just assume that they're the same, and then there's kind of almost classical situations where they're not. So you have to be careful. But what we want to take is these vertex algebras, which I'm going to call C real greater than 0 graded. So first of all, they are generated by their omega space. And this is saying that this notion of degree is well-defined, and it's assumed that it's well-defined in Labor-Mason, but in general, you have to be a little bit careful. So you could say, like if you were going to induce from the Jou functor, let's put our omega all at degree 0, right? Or your Jou module that you're inducing from at level 0. Put all of that in degree 0, and then define the notion of degree based upon this notion of weight in the way that you would naturally do. This is not necessarily well-defined, but if it is well-defined, those are the types of nice vertex algebras I want to grab. Right? Okay. So degree and weight compatibility. Why the name? This seems like an odd name. I'm just saying this degree versus weight coincides and is well-defined. Well, it is assume, basically, in Labor Mason, but we then prove in our paper that for such vertex algebras generated by omega and degree and weight coincide, then either, for all of your non-zero vectors here, either you have the real part greater than 0 for this degree, or it's 0. Hence, you have this type of grading right here. Lovely. So that motivates that. And then it's a proposition that, in fact, the 0 degree space and the omega space coincide. Now, at the risk of derailing myself completely, if I take my weight corresponding to my L mu here, we have in this strip, we will find that, and I'm going to call these different structures mu m. This is just this space. Outside in this very badly behaved blue area, this has, see, sorry. Here, you do have, for instance, omega mu m is your 0 space, but it's infinite dimensional. Okay, and then I don't want to go into it, but bizarre things can happen here. But in the entire strip here, including outside of these two dots, including these lines outside of these two dots, and including my nice orange area, you do have this nice vacuum property. But the blue area is just crazy. Yes? Uh-huh.
Isn't this the algebra and the weights of the two generators for mu and 1 minus mu?
Yes.
But isn't that symmetric in beta and gamma?
Yes, that's the line. That's this line.
Right,
This is.
So what I don't understand is why the weights at 1 is not infinite dimensional.
It is.
Weights, yeah.
It is. I'm ignoring. I'm just. I can ignore.
So that strip is the internal though.
It just flips.
Yeah.
Well, it flips. Yeah. Okay. Okay. So let's talk about conformal things. We have not. I haven't added the conformal at this point, although I just spoke about it a little bit there. So we have the notion of a conformal C-graded vertex algebra, where I have my conformal vector, and its modes generate a representation of the Virasoro algebra, blah, 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 blah. Are things in the orange area? Things will be in the orange area if and only if they satisfy this. So I'm just going to call these nice VOAs at some point. Nice VOAs. They're not VOAs. They're C-graded. But they're generated by their omega space. They have some nice positivity. They're, positive energy module grading, if you would like. If the physicists won't kick me out of the room for saying that could be a grading with respect to a graviton. With respect to a Laplacian, I apologize. But hey, I'm in a math conference, so I can say that. So you want some of the nice things. And one of the things that we are doing right here, which in general you can, and Labor and Mason talk about, even their vertex algebras, the conformal structure might not grade via eigenspaces, but generalized eigenspaces. But we're just going to do, for the purpose of this talk, just eigenspaces, finite dimensional. So that's why oh shoot, what did I do? I'm okay. I went back. I hit the wrong thing, you guys. That's okay, I need to slow down, right? This guy this guy falls outside of this definition. So these 2 points are not in there because it has infinite dimensional weight spaces, but that's all. These guys fall outside because they don't satisfy 2, condition 2, which is basically a condition that I want in order to be able to say that my vertex algebra is a nice module over itself. And my claim is that these are very, very nice VOAs if you forgive them for not being integer graded. And many of them, if I'm on this real line, they're just rational, graded by rational numbers. There's your picture here. And all of these there's easy examples I've already given some examples of things that are in here, but not in here. So I start off with a vertex algebra. I put a C grading. I say that it's generated by omega. And then I want to put 2 things on it. I want to put a conformal structure and say that it's real greater than 0 graded. But the intersection of these guys is not our guy, because we have examples down here. Okay, so these are our nice guys. And then for VOAs, we would, this would be our containment. You use vertex algebra, you make a Z grading, you take a conformal. Okay. So the theorem is that if you're in the orange region, then you have one of these nice guys, and your 0 space is just your 0 degree space is your omega space. It's one-dimensional. They're well behaved. In fact, they're very well behaved. The blue region, we do not have that these 2 are equal. It's not a strongly generated. It's not generated by its omega space because it would be 0 then. If you take the 0 one, I guess. Okay. And in the remaining regions, so you either have that the omega space is the 0 degree space, which is just the vacuum, or you have that they agree, but they're infinite dimensional, like in the standard beta gamma system. Who knew? I looked at beta gamma. I never did anything with beta gamma, and then I started looking. It was like, does anyone do this? I don't know. Okay, so nobody had done it, so we did it. Okay. Now, we got to talk about modules because, and this is where it comes. So we have this whole family of vertex algebras with whatever kind of bizarre conformal structure you want to put on it, almost. You can't make it into a regular VOA. But then you have to ask yourself, what modules do I want to look at and why? So all the modules that you see in the papers on beta gamma are modules for each one of the, no matter what mu is, it's still a module for that. It's just it might not respect the conformal structure that you put on this or the grading structure that you put on this in some kind of nice way. So for the purposes of this talk, what we were going to focus on is what you would call admissible modules, and Labor and Mason call them admissible modules. So admissible module is one that is C real greater than 0 graded. It makes it so that your vertex algebra is a module is a C real greater than, is an admissible module over itself. It makes it so that your vertex algebra is an admissible module over itself if it's in this nice orange zone. So if you focus on these modules and you define the omega space, a space of lowest weight vectors, or if you want, in the way that you should, then the following is stated in Labor Mason, but you need all of these some added assumptions and subtleties, I think. But we go ahead and say, yes, then your nice vertex algebra is a graded module over itself. And if it's simple, then this 0 degree space for your admissible module is equal to its lowest weight space. So, for instance, it would be induced by a Joux algebra appropriately defined. Okay. Then an ordinary module should be that it has a weight grading by eigenvalues, eigenvector space with respect to your L0 operator. These are finite dimensional. And you have this nice the real part of this lambda is greater than 0 for all but finitely. I mean, here I should point out, I've moved from the VA setting to the really nice VOA setting. Right now I'm talking about compatibility of the degree structure, which is all we had for the vertex algebra, with the conformal structure that now we've added that is also now has compatibility with the degree grading. And then we call our omega generated C real greater than 0 VOA, our nice complex VOA, rational if the category of admissible modules is semi-simple. You with me? Have I lost you? Questions? Our theorem is that if you have one of these nice guys, and now I'm saying generated in the usual sense, finitely generated by V1 through Vk, meaning it's generated by the modes of these guys acting on your omega space. If that's true, but these are not of integer weight, so they can still be rational, for instance, if you are unhappy with complex or uncomfortable. It can still be rationally graded. I have some kind of positivity condition that I'll talk about in a little bit. I haven't even defined this V upper 0, but it's the things that are integer graded within your vertex algebra. And I need an extra condition to prove this. Every simple is ordinary. Then, this can be proved in many cases where you have like some other structure like a finite automorphism. Then I can use twisted modules to prove that, in fact, simples are ordinaries and things like this. So it's not such a strong condition. Okay. Then V is rational and, in fact, only has one simple. I'm going to define. These are the things that are integer graded. Integer graded.
Yeah, but so how is that a condition then?
Yeah, it's just it always happens in this context.
So I don't understand what point number 2 in that theorem is. Is requiring something or is just defining something?
No, it is requiring something. Yeah, I'll define it in a second, and we'll see if you're happy with it. There's a counterexample if I don't have this on here. Okay. So, application of this, along with, I haven't proved 3 for this setting, 0.3, but if I'm in, this is just the orange region. If I'm in the orange region, this is one of these nice VOAs, if and only if it's in the orange region. In this case, you only have one simple, which is ordinary, in fact, it turns out. And it's completely rational. I don't think I say that there, but that is the result. The proofs, and the reason is that V upper 0, strange thing, is that the machinery involves Joux algebra, filtration of Joux algebra, finiteness of what you would naturally call the C2 space in this setting, and then another theorem about once you get your hand on the level 0 Joux algebra, it's not enough to just say, okay, well that you only get one simple from it, but you still don't have rationality unless you have this added condition that simples are ordinaries. And in our case, our application that we're doing today for the Weil algebra actually does satisfy that. So we have rationality in the sense of restricted to these to admissible modules for this C-graded vertex operator algebra structure. Okay. How much time do I have? I have time. So, and the game is, you just follow your nose with what you would do if you were defining Jew-algebras in the twisted setting, right? So we have the notion of Jew-algebras for the twisted setting, and in some sense it focuses on the zero eigenspace with respect to the automorphism, right? You break everything up into your vertex algebra up into eigenspaces with respect to this finite order automorphism, and then you basically throw everything out except for the zero eigenspace, the fixed point algebra, and Jus gives you the information about those types of modules that are admissible for that fixed point algebra, the twisted Jus algebra. So imagine doing the similar thing, but now I'm dealing with complex graded. Same difference. And this is completely following Labor and Mason. Thank goodness, because I don't want to go through all the details. No, we checked. Okay, so I define the ceiling then of the difference between the weight and the, so I look at the difference between the weight and the nearest integer to define the V upper R as this discrepancy. So I can, in this setting, engineer it that this has a is bounded below. And that's all I need, actually. I've actually simplified this where at some point it's this V upper zero space that we say is n-gradable. So bounded below. Okay. So this is some vertex subalgebra of V. And you construct Jus algebra from that. So everything works out nicely. I define my circle product based upon the ceiling. I define my product based upon the, this should have a ceiling on it, I think. And that's a typo. And then we define OV to be the elements generated by this. And under, and it's a proposition in Labor-Mason, that if you are outside of what you want to think about as the zero eigenspace in this case, but the integer graded piece of your vertex algebra, then you're in the module that you're modding out by. And this is just a long slide showing that everything works as it should for under Labor-Mason. I guess it, yeah, okay. Yeah, this is not a typo. I said it was a typo. It's not, it's just that the residues of these things are going to be zero. So if this is not integer, the residues here are going to be zero. So it's just making everything trivial unless you're in V upper zero. Reimundo, you look worried.
Oh, no, I'm just trying to understand, but this answers my question, right?
Right.
I just want to understand this U bar, the definition of the
Right.
ceiling of the real part.
Right, that's all it is. Okay, this is just a slide saying that we did our due diligence and we read through Labor and Mason. Everything's fine. And I can define a Jus algebra with respect to this grading. One that naturally has an induction functor so that all of our simple AV modules, this is a slide saying everything works so nicely, that this is the Jus algebra you want, that if you call the modules that we took before as these admissible modules, then these simple admissible modules are induced from AV modules in the natural way that you would. And everything holds up nicely. And in fact, you're just looking at things in V0. And so assuming that you have a bounded below situation, I can now start my filtration. So I want to relate this to some V mod some finite space. So these guys, nobody here is C2 cofinite, right? Nobody. So I have to look at what is going to naturally come up in terms of seeing my vertex, my Jus algebra in the graded filtration setting. Okay, so I take this filtration. I notice that my my multiplication within my Jus algebra behaves nicely with respect to it, and thus I have this. And defining this, then we have a associative structure on my Jus algebra as a graded vector space. I'm going fast now. Stop me if I should go fast. We can't go through the details anyway. This is, okay. So then, and this is in fact a commutative associative algebra, isomorphic to AV as a vector space, and one can show, so this is all work of ours, doing the filtration and setting up the filtration, and mainly Gail Yamskulna, she's a titan with respect to these types of things. So she led the charge up the hill, and here we are. And here is the space that you want, which you may feel like throws away too much, but we do the same thing with twisted modules, right, if you think about it. And we have our C2 condition for U in our integer graded setting, and then we throw away everything else. we say that if A and B are in V up are not equal to 0, then they're in CV, as they should, because if you're going to want to make it isomorphic to our graded Jus algebra. And under this map from V to graded AV, these are in the kernel, and this induces a linear epimorphism so that we have the dimension of the Jus algebra. You're just following at this point what Jus originally did, right? But you also do in the twisted setting. So you have dimension AV as less than or equal to the dimension of BCV. This corollary just says everything works nicely. Going to skip it. Okay, so there's some work of Gail Yamskulna, and then also with a student of hers, where they look at these strange lattice settings where you're in the twisted setting in this case, but you have some kind of non-positive definite of your lattice, and if you do not assume some kind of positivity grading and you try and do all of this, you get a bizarre thing happening. The title of my talk could be Bizarre Things Happen. Okay, so here's a bizarre thing that happens. Here you have, if you define things normally, you have that your C2 algebra, the dimension for the Poisson structure is 0, but the Jus algebra is not. A whole class of things. You know, monsters lurk everywhere, I guess. Okay, so we can then prove that if these are non-integer graded, then this Jus algebra is one-dimensional, because this, and it just follows from the fact that the Poisson, this V mod C, is one-dimensional, and so you only have one simple. And in fact, the VOA itself, it's not enough though, right? This is not enough to say rationality or anything. You have to prove complete reducibility. But in this case, because the Jus algebra is so trivial, is so nice, we can prove a theorem completely different setting. Let's say you have one of these generated by omega, C real greater than 0 VOAs, such that every simple is ordinary. That's where I have to put in that extra condition in our result, but it follows for free from my beta gamma system, for instance. AV is a finite dimensional semi-simple associative algebra. That's a pretty strong condition, but we have it in our case, so if I say that, and this by the way, we kind of cribbed from the, some work by Dong and Nagatomo in a completely different setting. We saw that there was this proof where they assumed some of these conditions, and I forget if it's the twisted setting or something else, but we just, we could do, this is our setting, we can play in this fairly restrictive setting and everything, because now I'm requiring that you only have one eigenvalue, that for my Jus algebra, it acts via its 0 modes on all irreducible AV modules as the same, and so because we just have this one copy of C, we can put ourselves in this setting, we prove this theorem, and then our two main theorems follow. And interestingly enough, it is exactly what you need to use again and again and again and again for this setting for our nice C-graded VOAs is this compatibility of the omega space and the degree space. The compatibility, you have to have this compatibility of your C grading with the natural degree grading that you would put on the space arising from putting your omega space as, inserting it as being degree 0 as you would following Jus.
Are there any questions for Katrina?
Maybe it's a naive question, but at some point you define the strong generation, omega strong generation. But usually when you have in Vertex algebra theory, when you have strong generators, you only take Fourier modes with negative coefficients.
Yeah, that's why the term strongly generated is a terrible term. I do not mean that at all. When we started taking the finite generating, generating in that sense, finitely generated by, I mean that these are the negative Fourier modes acting on this omega space where this very unfortunate term strongly generated is being used. So it's not in the sense of Andy Lenshaw's talk that you've already seen, and I apologize for the confusing terminology. It's Mason's terminology. So.
Question that perhaps is very silly, but I will ask it anyways.
Well, we'll just laugh at you then. No kidding.
There's a construction plan of the usual Jus algebra, the differential rate, that doesn't use a conformal structure. You just take a residue by multiplying by a particular exponential function. And then, if you pick any conformal structure in your vertex algebra, the corresponding Jus algebra is isomorphic to this one, that didn't depend on the conformal structure.
Yeah, so, and in this case, the level 0 Jus algebra doesn't depend on the conformal structure. It's only in the higher level Jus algebras that you need to know what the conformal structure is, because you need to, because the 0 modes for the omega are already in the circle product. You're already modding out by them. So it's completely, it doesn't matter at all. So here we definitely are not using the normal notion of Jus algebra.
Yes, so my question is if you have a Planck's construction for these algebras.
No.
Something that doesn't depend on the conformal structure that you chose.
No.
It does, but in a different way.
No. I mean, so the Jus algebra, like, and here, this is here the Jus algebra is a viral algebra. It's completely, like, it's surprising to me. Like, so here you have a normal Jus algebra because you have Z grading. Okay, you have infinite dimensional weight spaces, but that doesn't matter at all for the Jus algebra either. So you can define a Jus algebra just like normal, and it's the viral algebra, and then you have a gazillion, gazillion modules, and it's irrational. But you can find, and I encourage you to look at the work of Alan Wood, Ridout Wood, so showing that there's a nice class of modules that you can have some nice fusion rules, closed under fusion, rigidity, all sorts of stuff. So all the fun things that the category theorists want. But as soon as I come to here, what am I doing with the Zhu algebra? I'm looking at, residues with respect to the integer grading, and so the only natural, part of the theory, the moral of the story is that we need better things than Zhu algebras, or higher level Zhu algebras even, right? It doesn't play nice with this picture at all, right? So I can conformally flow easily from something that is a very, very different structural to something very irrational to something that's very rational in any kind of normal sense of the word that you would want, back to irrational theory. And then I could go out here and strange things happen. Here you don't have positivity grading. You don't have this sense in which, because you lose complete control over the imaginary graded pieces. They go infinite in both directions and are not controlled in any way by the real graded part. Up here, even though I have non-imaginary, I'm still controlled by the real grading, this nice grading that we have. I don't know, it's a very bizarre picture to me. I was very confused when, but I'm just passing along the strangeness at this point. Yeah, we need other things than Zhu algebras to understand some things in the world. Induce modules that we may be interested in other ways than Zhu might see.
So if there are no other questions from people in the room, are there some questions on Zoom, Jethro? No? Okay, so perhaps we can thank Katrina one more time.
Thank you.